In this section, we're going to take a look at kind of what is like the core underlying idea for this entire chapter, which is the concept of partial derivatives. So what exactly is a partial derivative? What are we talking about with this? Well, let's take a look at what we have here. Suppose that a surface given by a two-variable function maybe looks like the picture here at the left, or maybe it looks like a more complicated sort of function like the picture at the right. Now, on this first picture, the one with the flat plane, you'll notice that I'm highlighting here a particular point that has some set of coordinates. Let's suppose it's got coordinates, as I state here, A, B, C. And we can imagine like a similar point maybe over here on this more complicated looking function. All right, so what I'm interested in trying to do here is to understand two different possible things. First, what if I was interested in knowing the rate at which the z-coordinate on the first surface is changing? Now, one thing that you might notice right away here is that if this is a perfectly flat plane, then no matter where I kind of move the point in any particular direction, my z-coordinate isn't actually going to change at all. Whereas in the other picture, if I was to move this particular point around, my z-coordinate might go up, it might go down, it might go up quickly, it might go up slowly. It kind of varies and depends on where the initial point is. So what can I say specifically here about this point? What is it that I'm really going to focus in on measuring? So specifically, I want to look at how much the z-coordinate is changing, but we're going to start by looking at if I was to kind of move that particular point parallel with the x-axis. So you'll notice here that my x-axis is kind of running, I guess you could say, like front to back on the paper, and that would kind of fall in line with where this brown curve is. So I'm imagining if I was to redraw that point or shift that point and drag it along this line, how would the actual z-coordinate change for the surface? You can imagine the same sort of thing being done over here, where I could say that if I was to move along in the x direction here, I'd be kind of dragging the point kind of along this particular grid line that I have here. Okay, so you can kind of see it's got like almost like a parabola-y sort of shape. Okay. So this is this amount of change is one of the possible changes that we're going to be interested in. So since we're looking for how much the z-coordinate changes as we kind of move along these individual black curves, that relates back to a Calc 1 concept. Really, what we're looking at is we're trying to find the slope of a tangent line as we move along these individual curves. So I'll write that here. That is, or this means, we want the slope of the tangent line at P along the black curve. All right, so that is along those curves that I've sketched there. So that's really what we're looking for. You can kind of imagine that in the first picture, the slope of the tangent line is going to be perfectly flat because I have a perfectly flat line there. As opposed to in this function, if I was to draw out a tangent line, I could imagine that it might have a non-zero slope at that particular point in time. Okay, so I am interested again in trying to find these slopes of tangent lines. And in the first case, we looked at that z-coordinate change as we were kind of moving parallel to the x-axis. But we could do the same thing and ask for the z-coordinate change, how much is that changing, as we move parallel to the y-axis. So that would be kind of like moving along this red curve that I'm sketching here. Or if I was to kind of draw this in the more complicated picture, you'd see I get this like really weird function that kind of starts high and then like drops off this ledge over here. And notice if these were the curves that I was looking at, and I wanted the slope of the tangent line on those, I'm going to get a very, very different sort of curve. Here I'm going to get a very, very different sort of tangent line. Here I would get a tangent line like maybe sloping in a very opposite sort of direction to what the blue tangent line is. Now in the other picture, I'm still going to get 0 back because my plane is perfectly flat. But either way, if I was moving parallel to the y-axis, what this means is we want the slope of the tangent line at P along the red curve that we sketched. Okay, so this idea is what's really crucial to understanding the concept of partial derivatives. This kind of slope of a tangent line, but looking at the curve or shifting our point in a particular direction, either parallel to the x-axis or parallel to the y-axis. When we can fully understand this information about a particular surface, we can start to understand how the surface overall is changing. Now, if we're going to start to define more rigorously what a partial derivative is, we're going to define this derivative via a limit, much like we defined derivatives back in Calc 1. So here you'll see I have this big, scary limit definition that should be reminiscent of things that we talked about back in Chapter 2, but also that limit definition for a derivative you discussed in a Calc 1 class. We're not going to use prime notation here to notate our derivatives. Our most common notation that we're going to use is subscripts. We're going to have f with the subscript of x to say that we're moving our point along the black curve. We're going parallel to the x-axis. And we're going to go ahead here and say that fy would be like moving along a red curve and then measuring the slope of the tangent line along there. So you'll see here that both of these are defined with a pretty similar limit with one unique sort of difference. If you take a look here at the first limit that I have, you'll notice that I have this f of x plus h minus f of x, but like this y portion is remaining constant. This should represent then exactly what we expect, because again, our limit back in Calc 1 looked something like this. It was f of x plus h minus f of x over h. And we have the same basic structure here. Notice though that the y is not changing and doesn't have any modifications to it, because along the black curve, y is constant, right? I'd be locked in at a particular y coordinate, call it b, this entire time. The y coordinate for every single point along this curve is b. So in this case, my y is a fixed value. It's like a number. And in much the same way, when I get over here and I'm doing my partial derivative with respect to y, my y is varying, but my x is constant. Just like how up here in this picture, along the red curve, my x would always have the same value, call it a. Okay. So again, f sub x, or what we call this partial derivative of f, with respect to x, represents a rate of change of the z-coordinate when, with respect to x, when y is fixed, when y is locked in as a value. And we get the opposite for our partial derivative with respect to y. As we had seen up above, this fx and fy ultimately then correspond to slopes of tangent lines along these particular curves. So the last thing we're going to talk about in this video is some of the important notation that we're going to see. We actually have many different possible ways to represent derivatives, and there's going to be two main ways that we deal with these representations. The most common representations that you're going to see in our class are going to be this partial derivative notation with subscripts, and also in this kind of Leibniz notation. Notice here, I don't have what I used to write in a Calc 1 class, which is something, say, like dy dx, but I have something very close. I just kind of have this curly d going on here, and that represents that I'm dealing with a partial derivative, as opposed to like a full regular Calc 1 derivative. Again, the reason that we're having to do a partial derivative, and we can't necessarily have a notion of a full derivative, is that our curve changes its z-coordinates at different rates, depending again on which direction you're moving in with respect to x or with respect to y. So these again are the two common notations, but you'll see that these other notations here can also be used. So if you're ever watching something on YouTube or looking up something in a textbook and you see these notations, don't be surprised. They mean the exact same thing. In the videos to come, we'll take a look at some quick examples of how we actually go about computing these partial derivatives given a function, and we'll see that actually it's going to be really, really simple to do, assuming that we understand how to take derivatives back in a Calc 1 class.